I went for a UNDP program workshop in January this year. I had the same statement. And I think 2017, I heard that statement again. We all use plastics products. Currently, we are all drinking. All right. But after using the plastic, usually for water, what do we do to the plastics? In most cases, we just dump it. And we think that when we do that, it will disappear. And I can assure you that this culture is not only in Ghana. For a very long time, the whole world, including the superpowers, US, the whole of the European Union, have been pretending that they are dealing with plastics, when in actual fact, nothing was being done. On 30th January this year, at the conference that we went, we had some resource persons from Germany, moving all the way from Germany to Africa to talk about plastic waste. He made a statement that was very surprising, that of all the plastic waste that are produced in the EU, take all the EU countries, 60% of the plastics, they gather the waste and then ship it to China. And this they've been doing for a long time. And then the 40%, they will have to try and then deal with it. The others will be just disposed indiscriminately into the environment. In November 2017, China just came out with a surprising message. We have had enough of waste plastics, so we are not going to import any waste plastics again. Then the whole of the EU realized that they were not dealing with plastic waste, but they were just always looking for a convenient way out by just gathering everything and then shipping to China. I want to show you a small thing that we have done. I'm showing that video that is just about 1.5 minutes, because I think it cuts across all the disciplines over here. Then I'll go to the main presentation. You see sachet. When was the last time you separated your sachet from your waste? I don't think we care. We want to know what happens to our sachet. We drink the water, and then after that, to hell with it. I don't care what happens to it. And this video, which is just about 1.5 minutes, is on, I think, YouTube, and then several. One that decided to put it on my Facebook, and then within 3 hours, I've had about 4,000 views. Let's see what is there, please. I just want to demonstrate to you that we can create values from waste. Every plastic that was produced from crude oil. So when you drink your water and then you throw your plastics away, you are throwing crude oil away. That is deserved. We have tested the properties, the flash point, the pour point. We use GCMS spectrometer to test for the properties, the density, and then we realized that we're producing something from diesel, aviation fuel to kerosene, depending on how we vary the type and amount of catalyst. This is a very simple process. What do we do to our plastics? The waste is now becoming because they realize that if they are not careful, they are going to be consumed by plastic waste. Now today, this is just something we did. We're there, we're doing our own thing because we are from the minerals engineering department. I am a metallurgist. So I deal with metal. One day I was just there and I decided, well, let me see, because I know that we produce plastics, diesel, plastics are produced from diesel. And we is it possible that I can produce the diesel from the plastics? We just set up something simple. The first day I put the equipment there, somebody was passing through and he asked, are we going to produce aquatation in the lab? I said, no. When we start producing what we want to produce, you will see that sometimes we can use something from our own traditional way to produce things in a big way. We are currently developing this process. Now back to our technology. Ghana has, in fact, for all the governments that we have had from 1970, if you go to their drawing boards, there is something they had always wanted to do to produce our own iron or to come out with an integrated iron and steel company in the country. Since 1970, the present government is currently interested in setting up its own iron making facility, as well as to add value to our bauxite. Because we don't want to continue to sell our bauxite at $30 per ton and then go back and sell it and buy it at over $400 per ton to come and feed Valco. So Valco will struggle. The conventional way of producing metals, aside of gold, because currently, as far as gold is concerned, Ghana, I think I think we are okay. I don't think we have too much of an issue with gold. Because if you compare globally, I think, so in terms of gold, I will always say that the normal, recently, very good mining process. But we'll get finished one day, whether we like it or not. What happened at Angugu Ashanti, and then what is currently going to happen at Prof. One day we'll wake up and then we'll get more gold. But ask ourselves whether we are ready. We have several other metals. And I am doing a polymer reduction technology that we have developed new much over here, which we have at so many conferences, published extensively on them. I just a bit of it to see how we can use our plastics to our own advantage. I am going to take you through just an introduction and then some small experimental work. It will capture everything that we have done. Please go to the next slide. I am giving you an advanced country like Australia, what they do with their plastics. You notice that the most widely recycled plastic is what you are using now, the PET, polyethylene terephthalate. That's the most widely recycled plastics. Globally, around about 50%, if you put other countries together, is recycled. It means that the other 50%, nobody knows what happens to it. Then we have our high-density polyethylene, HDPE. In Ghana, a typical example is the sachet that we drink from. People think it is LDP, but most of them are HDPE. Globally, in Australia, it's around 23% currently. Then we have our LL and the LLDP, your shopping bag. Whenever we go to the, like your shopping bags, they are made of low-density polyethylene. Our polypropylene, your trash cans, your buckets, your bowls, and so on and so forth. That one, around 18.1%. But there are some plastics that have low recycling rate down to about 5%. It means that we are only able to recycle 5%. The rest is just allowed to go where it's supposed to be. The rest is usually landfilled or dumped illegally. And I can assure you that a lot of them will end up in the oceans. It is estimated that by the year 2030 or 2050, there will be more fish in the there will be more plastics in the ocean than fish. So we are gradually heading towards a situation where fishermen will go fishing and then they can only come out with plastics and not fish. In Ghana, what is the situation in Ghana? As of 2005, an estimated 270 tons of plastic waste generated every day in Ghana. Out of this, 85% will come from the non-biodegradable plastic bags. It means that they can stay in the environment for about 500 years, nothing will happen to it. Now, the issue about plastics then is the inhomogeneity of plastics. They come up. If I go to the municipal solid waste, I have several varieties of plastics. Now, current ways of recycling them is such that you require plastics to be sorted out. And that is an issue because it is both uneconomic and usually is said to be unhygienic as well. I don't think you want to go to the rubbish dump at here, and then you want to go physically go and then sort them out. You wouldn't do it. So trying to sort out is expensive. And that is why we have to try to make sure that the plastics do not get the municipal solid waste stream. Otherwise, the opportunity is lost. I have not thrown any plastic waste away since 2012. And at home, my family knows that it is a taboo to allow plastics to go and then mix with the other waste stream. We don't do it. And I wish that as you live here, you carry this message to wherever you are going. Let us try and do something because there is a danger that is looming. If you're not careful, we are going to be consumed by plastic waste. Now, what the work we are doing over here, in metals production, we do what is known as a carbothermal reduction. You have the metal oxide, and then to produce the metal, you need something to take the oxide component, that is the oxygen. So that you have the metal being there. That is done by carbothermal reduction, which means that we need something that contains carbon to be able to do that for us. In most cases, we use what is known as metallurgical coke. And this metallurgical coke, in Ghana, currently as we speak, we don't have any. So if we were to set up an iron making company in Ghana, we need to go to countries like China to be able to import metallurgical coke to produce our iron in Ghana over here. But what is in metallurgical coke that is responsible for the reduction? Metallurgical coke is important because of the carbon. Now, the problem then is that in Ghana, we don't have metallurgical coke. And also, it is expensive. Even if we were to go and then import, it would be expensive. Now, the good thing is that the plastic waste that we throw from your polyethylene terephthalate to your high-density polyethylene to your polypropylene, they contain what metallurgical coke contains. The advantage of the plastic waste is that aside of the carbon that they contain, they also contain hydrogen. Now, in terms of ability to remove oxygen, hydrogen also has that advantage. So we decided then that we want to come out with an iron-making facility in Ghana that will rely entirely on waste plastics and then other carbonaceous materials in Ghana. This is the iron-making route by what is known as the rotary heart furnace approach. This is something that is alternative to the blast furnace iron-making process. It's a very simple technology because it does not rely on the grade of the ore. It means that it is configured to handle even low-grade ore. The next step. And this is a scheme of the rotary heart furnace process. We went for this and then we decided to simulate this in our own lab. In the process, what you have is you have the whatever the pellet, and then you heat. Once the pellet is sufficiently heated up, the carbon in the pellet will take the oxygen and then you produce your metal. Next slide. Now, so we decided that we want to use our plastic waste, but the waste was from mixed plastic waste because we didn't want to sort them out. Sorting out is expensive. Okay? So we're able to produce our carbonaceous materials from the plastic waste, and then we use the carbonaceous material as a reducing. This was applied to the shiny iron ore in Ghana. You know that we have an iron ore in Ghana known as the shiny iron ore. It's in the northern part of Ghana. We also have one known as the Opomansi iron ore in the western region. There is one in the upper west region, the Pudo iron ore. And then there is a small one in the bottom known as the Akwafutuji iron ore. We have tried our technology on all the ores and have been able to produce a lot of metal using waste plastics. Sometimes we mix with biomass, and so on and so forth. Sorry. So even where our waste plastic is in shortage, the technology is configured to be able to mix your plastic with things like sawdust, palm kernel shells, coconut shell, and so on and so forth. Let's see part of the experimental work that we did. Materials that we used were the shiny iron ore, your high-density polyethylene, your polypropylene, polystyrene, expanded polystyrene, your PET, and then your LDP. Your polystyrene is when you buy your fridge, and then you remove your fridge from the box, not quite styrofoam. It's your polystyrene to expanded polystyrene. If you go to the restaurant, your takeaway food containers are all made of polystyrene. Polystyrene, for example, contains about 92% carbon. The rest is hydrogen. So when you throw it away, you are just, it's very important away. Your sachet contains about 85% carbon and then up to about 14.5% hydrogen. So it's something that is ready. do whatever you want it to do for you. Now, how do we, the basic issue is with getting the plastics in the form such that it can do the work that it will do for you. I am going to show you 3 ways that currently is being done globally. Now, the first one is cryogenic pulverization. Cryogenic pulverization. You need liquid nitrogen. Nitrogen is always a gas, but sometimes you can get it in the form of a liquid. So it means that the temperature should be very low. And then you put all your plastics in the nitrogen. That will render the plastics to become brittle, and then you can easily pulverize. You can also use something known as the cutting mill pulverizer. This is a technology developed by UNSW, Australia, where I did my PhD. Now, we in Ghana said that we cannot afford, especially in our lab, because of the cost and the inconvenience. So we decided we want to use some heat treatment process to achieve the same thing. So we used a heat treatment process, and then we're able to come up with plastic, the form that is needed to do the work. This is the cutting mill pulverizer in Australia. You can move on. So this is what we did. Our pure water sachet, we're able to pulverize it to, oh my God, the pulverized foam. Our PP bucket, we also able to get something in the form of powder. A very simple process in our lab. You take bottles and then your vener, and then depending on the brand, we're able to get it in the form as you have over there. In our shopping bags, we were able to pulverize it. To be able to see whether it took the plastics through what is known as a thermal decomposition process. Now, you talk about thermal decomposition, you're talking about high temperature. How is the plastic going to behave at those high temperatures? If it is able to produce some gases or solids that can do the reduction process, then that plastic will qualify for the process. And to do that, that is how we went about it. We mixed it with alumina because alumina will not reduce at those temperatures. And then we measured the gases that came out. Now for the reduction studies, the iron ore was mixed with the plastics in the same way as we did the thermal decomposition process, so that this is ready to be heated in any heating source. Come on. This is a horizontal tube furnace in the laboratory somewhere in Australia. We didn't have one here, so we were able to start with a domestic microwave. Our ladies, and then the microwave that we use in our rooms to cook. That was what we used to get the heat source. To do our reduction. Now, this is what happens in the reaction zone. Very high temperatures, you heat your whatever, and then your pellet, and then you produce your metal. You can move on. So your metal, your pellet is placed in the heating zone, and all you do is that you heat for between 2 minutes up to about 40 minutes, depending on the ore and then the mixture. And you produce your metal. I have produced metallic iron. I check the grade about 99% within 2 minutes by just heating. You just put it there, and then within 2 minutes, I just bring it out, and then I have produced my metal. But that means that you have to have an effective source of heating. In Ghana here, we are able to produce iron from about 10 minutes up to about 10 minutes. We have tested the iron. The grade is the same grade as we had in Australia. The conventional way of producing iron would take about 1 hour in the blast furnace. We are able to produce iron in less than 30 minutes using waste plastics in Ghana. Let's move on. So the results and discussion, I wouldn't want to bother you too much of the details and that, but so we'll just flip through and then you see the sachet. As unfortunately, we are working within time, so now let's look at the results. We wanted to be sure that whatever material we are using is exactly what we are using. The sachet. I hear a lot of people saying that the sachet is LDPE. So we tested, we decided to do it. A scanning electron microscopy, and then we did an XLD, X-ray diffraction analysis. An XLD is like a fingerprint. It tells you what is there. Now, high density polyethylene, we know, is a crystalline or semi-crystalline polymer. Accordingly, when you examine its peak, you see areas having very sharp peaks. If you examine its diffractogram, the XLD is what we have over there. As you can see, you see those two sharp peaks over there. What you see, H4, which is the ethylene molecule. Now we're talking about high density polyethylene. That have been allowed to polymerize to form those molecules. So XLD revealed that was actually our sachet was actually produced from high density ethylene. Please move on. Now I went to PP. This we got from waste bucket. Our polypropylene is also a semi-crystalline polymer. It's a semi-crystalline polymer. Having the monomer CH6. So it's the propylene molecule added piece of surfactant to form your polypropylene. See over there. You see several peaks of C3H6. Next slide. Then the Vortic bottle, the Venner bottle, so many trade names that we use, which we are very comfortable. It's an amorphous polymer. That one doesn't show any peaks at all. So we did it, and then we saw that it was a PET. Next slide. Our thermal decomposition process. We did our thermal decomposition, and then we measured the gases that were coming out. We polymerized, we did thermal decomposition up to temperatures from about 0 degrees, 25 degrees Celsius, up to 1,500 degrees Celsius. We wanted to see what is happening. Now, these are the gases that we had. Please, yeah. The gases consisted predominantly, the white long thing that you see at the top is carbon monoxide. And then we have a bit, the yellow thing is carbon dioxide. You see that the carbon dioxide is very narrow. It's almost background carbon dioxide. So it doesn't produce carbon dioxide at all. I mean, with the HDP, okay? And then we also had some amount of methane. When I am producing diesel, I heat my plastics. And then my plastics is able to change into a vapor or a gas. Now, these are heavy gases that I can catalytically break down to produce my diesel. But this gas, I'm sorry, I tend to normally, when I'm talking, just want to be free. Now, the gas contains something that cannot be condensed, and that is methane. So whenever you heat your plastics, you always will produce methane gas. And then, because oxygen is present, you also produce carbon monoxide and carbon dioxide. Now, we are looking for three gases: carbon monoxide, methane, and hydrogen. This is what is known as an IR gas analysis, an infrared gas analyzer, and we're able to measure these three gases. Then we also were interested in hydrogen gas. Hydrogen gas couldn't be measured by the infrared gas analyzer. So we use what is known as a gas chromatographic analyzer. I'm sure most of you have heard about those things. And we're able to see large peaks of hydrogen. So we're ready. It means that our polymer contained the most important reducing agents that can our iron oxide for us, our carbon monoxide, our methane, and our hydrogen gas. And then it also left behind some solid carbon at the nanoscale, very fine carbon, which is also an excellent reducing agent. You can move on. Then we went ahead with our, as a result of reduction, when you're going on well, you are supposed to see a lot of carbon monoxide. As you can see, this was the reduction by the pure water sachet. Reduction by pure water sachet. You can move on. This is reduction by LDP. The white line alone is telling you that you produce a lot of carbon monoxide and therefore you are producing a lot of iron. Reduction by polypropylene. You can move on. Reduction by PET. Now you see that with PET, something else is happening. Apart from the white that we saw for most of the things, the PET is also showing some red. Now the red one is carbon dioxide. So when you use PET as a reducing agent, easily, some carbon monoxide, but you also produce some carbon. If I take my PET, 3% or 1/3 of the PET is made of oxygen. So if I'm using, it contains both carbon and oxygen. Then when I heat it, come out, and it can only escape as carbon dioxide. Let's move on. And then reduction by my pure waste sachet. Move on. We did the extent of reduction for this process. As you can see on the horizontal axis, the time ranges from 0 to 300 seconds. This to minutes. We are talking of 5 minutes. Now, wherever your line crosses the horizontal line at the top, your reduction is complete. I decided to compare this process to the conventional using the waste plastics and the mixed plastics. And I compared it to the normal material that is used industrially. So I was able to obtain metallurgical coke from One Steel Sydney Mills in Australia, the second largest steel producer in Australia. Now let's see how our plastics, the plastics that we throw away, compare with the conventional material that is used in industry. The red line is the reduction by metallurgical coke. All right. Now I see that the first line to cut the horizontal line is my mixed plastic waste. Now down there, it's about 120 seconds. So it means that when I mix my plastics and I use it as a reducing agent, I can produce iron completely in 2 minutes by the process. And it varies until I get to metallurgical coke. After 5 minutes, the metallurgical coke is able to give me just around 80% reduction. In 2 minutes, the plastic that I mixed was able to reduce my iron completely, 100% iron reduction. Now, this is to tell you that we have a technology which has often been ignored because the rest of the world felt that coke and coal was in abundance. We could just pack our plastics and ship it conveniently to countries like China. As you speak, I went online last week, and then for the first time, I saw that there was a researcher in UK saying that China says you're not going to buy any plastics again. Our search reveals that plastics can be used to produce metals. So it's a block, started talking for people to start thinking about plastics. The 60% that they were selling, we are talking about several millions, if not billions of tons of plastic waste that they need to contend with. What's in is, are we ready? You can move on to the next slide. This is a sample of the iron that we produced. Iron nuggets. That is the ore. Iron ore is red. And then when we mix it with the plastic, we form something known as a composite pellet. Now, this composite pellet is a reactor. Particles are pulverized to very fine sizes. So short, something that all it needs is process of heat. And then we put this pellet in a microwave. Trying to see whether we can get. We're trying to see whether we can get at least a laboratory what is it? A domestic, a laboratory microwave oven. We use a domestic microwave oven and it works easily. Within 20 minutes, we have produced iron. And that is a sample of the iron that we produced. We tested it. Some of them, about 99%. The rest is carbon. Every iron will contain some amount of carbon. We did an XLD. What do you see? You see Fe, Fe, FEC, FEC. So it's predominantly metallic iron, and then part of the peaks will contain a bit of carbon that it picked from the excess carbon. The reasons for the observed improvement, I think I've talked about it, because metallurgical coke contains only carbon and carbon monoxide. When I use my plastics contain the carbon that the metallurgical coke has. But aside of that, it also contains my methane, my hydrogen, and then my carbon monoxide. Okay? One thing that we have to realize is that hydrogen reacts faster than carbon. So when I use the conventional way, it's only the carbon that is reacting. But when I put in the plastic has the carbon, but it also has hydrogen. And they are all doing the reaction. So I will always have an improvement over the conventional way of reacting. I was interested in the environmental considerations. The carbon dioxide that is emitted. The plastics, aside of the carbon, also has hydrogen. When conventionally, one of the biggest issues that they are facing is that iron making is one of the heavy producers of anthropological carbon dioxide. And they are finding ways and means to cut down on the carbon dioxide production. That is where plastic waste will have an upper hand. Because when I have my plastic waste, I also have hydrogen. When hydrogen reacts with the iron ore, hydrogen will pick oxygen from the iron ore to form water vapor. So you see that the amount of carbon dioxide that is produced is decreased significantly because of the presence of hydrogen. And I saw that aside of having a better reduction, I'm also able to cut down on my emissions significantly. Move on. Then you can go down. Conclusions. We can use our plastic waste, whether single, whether mixed. We can use our plastic waste also mix with even the metallurgical coke itself, mix with coal, mix with biomass like sawdust, palm kernel shells, coconut shells. I have my students from North. They use peto waste, nut shell, corn cobs. We are using every carbonaceous material, and I can assure you we are producing a lot of metals. You can move on. I think that's all. And I think what is so we have everything in Ghana. We are ready to set up an iron industry. Probably, if not the whole world, maybe in Africa, to be the first country in Africa to come out with an iron making facility that will depend only on plastic waste. Look at the topic. I said, first, the topic was on application of waste polymer reduction technology in the production of metals. In this work, I showed that you can use mixed plastic waste. You can use mixed plastic waste. So when I go to maybe the municipal solid waste stream, technically I can use municipal solid waste to do my reduction, because aside of the plastics that are mixed, the plastics could also be mixed with some biomass material and then organic material and then the like. So it's ready. You can use it. The plastics in the ocean currently is an area of research that has gained global attention. A lot of monies are being sent in there by the UNDP and other funding agencies to find ways and means of maybe fishing for the plastics from the ocean. Once they're able to bring them out, we are ready to just go for them. And then, for example, if we were to go to Cape Coast or Elmina or whatever, any of the beaches, and then the fishermen, they fish. And then we have some interventions that we want you to bring out all the plastics, because that's the only way we can get the fish back into the stream. So once you're able to bring the plastics out, we can take the plastics straight away, and then we use it to do our iron making. Let me mention that so far you haven't heard about me talking about PVC, polyvinyl chloride, the plastics that are used in pipes and then the like. It contains chlorine. These are PVC, the metal chloride. We have developed a technology to deal with PVC, but for now, we think that we don't have. I'm sorry, I appear to be sinning by not using what I'm supposed to use. Sorry. We have developed a technology known as a dehydrochlorination process, where if you want to use PVC, we'll take the chlorine along with one hydrogen atom to form hydrogen chloride, which we can also sell, because hydrogen chloride can then be used in the production of hydrochloric acid. For now, we think that we do not have a large amount of PVC, and we have large amounts of other plastics waste, which we can grapple with for now. When we get to the stage where we need to go to the, we already have a technology where we can remove the chlorine before we can. When you take the chlorine in the form of, what we left is predominantly carbon, and then we can use it. We don't use the chlorine because when you have chlorine present at very high temperatures, chlorine is a corrosive element. You will corrode your furnaces, and then to be able to replace parts, it will affect the economy of the process. One other thing too is that if you have large amounts of chlorine and then you have plastics being present at those high temperatures, the presence of chlorine will lead to the formation of dioxins, furans, and then polycyclic aromatic hydrocarbons. These are potential carcinogens. And that is why we don't want to bother ourselves now with PVC. But we have a technology to deal with that. Thank you very much.
As the population grows, the use of plastic is going to get wider. And its control, I think, would be out of hand to handle. So what happens if the control is out of hand? I think there should be another solution for the use of plastics instead of encouraging the use of plastic. From what you're saying, it means that plastics can be used because there's a future to handle it. But what if it gets out of control due to overpopulation?
Several workshops are currently going on, and I want to believe that this is also one of the workshops. And I want to encourage you all to promise yourself that as you live here today, in your various homes, your halls of residence, and then the like, you'll find ways and means of not allowing the plastics to mix with the other waste. A lot of education is ongoing. If you go to Accra, I can mention several NGOs that is currently involved in education. In fact, first thing that we need to do is to educate the population. If our brothers and sisters who did not have the privilege of attending the university or maybe acquiring higher education, if they know that they can make money from plastics, I think the plastics that we tend to throw away will decrease. If the sachet water seller knows that if I sell my sachet water to a potential client, and then after he had drunk everything, whatever he or she is throwing away, I can still gather, sell, and make some money. The plastics will not get into the stream. This is food for thought for all of us. Plastic, currently we don't even want to use the term waste plastics. We use the term end of life plastics. It means that what you are throwing away is not necessarily waste, but it has served its purpose. So if I have the sachet, that drinking the water, the sachet cannot be said to be waste. It is an end of life plastic material. It serves its purpose for drinking, but then it's ready to do something that is even bigger. I don't know whether your question has been answered. Okay.
That's surprising.
Please, and our president's reign, His Excellency Nanado. We all know that he was much concerned about one district, one factory, and he wants to create more factories to reduce the unemployment rate. And also, I was moved by the video that I saw. So I want to know whether you've presented any petition which is in turn going to have any impact on unemployment rate or something which can help.
Thank you very much. I think I have a pleasantly surprising answer for you. Years ago, I would say no. But today, as I stand here, I will say yes. As I stand here, I am currently working on the commercialization of 3 of the processes. About on the day that UMAT was renamed George Grant University of Mines and Technology, the Honorable Minister for Environment, Science, Technology, and Innovation was in my office. I went to his office about a month or 2 earlier. So when he came to my office. I'm currently working on 3 of the technologies, namely the diesel production from plastic waste, an iron making facility for Ghana, and then a bauxite upgrading technology using waste plastics. That is also something that I did. We're trying to work on these 3 for now as part of the one district, one factory concept. I want to believe that it will become a reality and then jobs will be created so that people don't retire after 1 year of national service. Thank you.
Now it gets confusing when you have 2 ladies.
Okay. You said we are supposed to make a promise to separate the plastic from the normal trash. Okay, so let's assume we sitting here are able to do that. We are able to separate the rubbish from the other ways. There are people who are coming for the rubbish because we wouldn't keep it forever. The trash service or something, Zoom Live, will come for it. I don't know if there has been any or any public education telling them that they are supposed to separate the waste. So how sure are we that they wouldn't mix it when they are sending it back? Thank you.
Thank you very much. That is an excellent question. In fact, that is one of the questions, or that was one of the concerns that was raised on the 30th of January when we went for the workshop organized by MESTI, Ministry of Environment, Science, Technology and Innovation. Those who gather the plastic pickers, they will tell you that you go to Accra, for instance, you're able to put bins for plastic waste, for metals, for organic waste, and then like they do it very fine. And then Zoom Lions, big truck will come, you pick everything, mix them up, and then send them away. So that concern has been raised, and I can assure you that it is being given the needed attention. I think those who drive the trucks are currently also being given the needed education to let them be aware that it was for a reason why those things were separated. So when you go there and they already separated them out of convenience, just mix everything, then you have spoiled. It is already known, that concern is known, and it is being addressed. I have a feeling that very soon people are going to be educated and the right thing will be done. But education starts from us. One person can be an ambassador. It is something that is very serious.
Please, let's try as much as possible to mention our names, and then the question will follow.
My name is Desmond. According to My Joy Online, it stated that Ghana generates approximately 22,000 metric tons of plastic waste. And I'm to ask if you set up the company or the plant, and even if you are to process or to produce, to use the raw materials, the plastic waste, you have to use 1,000 tons a day for your production. It means within 22 days, the waste will be done. Would you get any raw material? So are you going to import the waste, or how are you going to get your raw materials for production?
Thank you very much. That is a very surprising figure that you mentioned. When we say polymer, when I mention the word polymer, it consists of several materials. I mentioned, or I talk about the flexibility of the process. That aside of it being used alone, it can be mixed with other materials. Typically, the sawdust that we throw away, the coconut shells that we currently want to just sell off, the palm kernel shells, the petrol waste. Have you also noticed that we have large amounts of vehicle tires? Sorry? I'm not saying. Large amount of vehicle tires. That is also one of the technologies that we have the slide over here. Currently, as we speak, we have globally every year 1 billion tons of plastics is produced. 1 billion tons of waste, what we call end-of-life rubber tire, is discarded. In Ghana, every vulcanizing shop that you go, several rubber tires that are thrown away, nobody knows what to use them for. Rubber tire contains between about 80 to about 86% carbon and about 7% hydrogen. So currently my MSc student and then 3 of my undergrad students are producing iron using waste rubber tire. So I can assure you that we have a lot of materials that can function as a reducing agent. We blend. And the surprising thing is that normally when I'm talking, I'll talk about the use of the polymers alone. But the secret in our technology is that it is the blend that does the work. And we have been able to develop a certain blend ratio for most of the plastics and then other carbonaceous material, where you have metallurgical coke completing its reaction in about 30 minutes. Your polymer, your pure polymer may bring it down to about 20 minutes, but a blend can bring it down to about 4 minutes or less. So the flexibility is there. Thank you very much.
My name is Ifya Safwa, and I wanted to ask a question about the video you showed. The process you used for the conversion of the plastic to the diesel, was that just a pyrolytic process or it was another process also?
Dr. Dankwah, please. I said during your presentation, you made mention of the environmental considerations you made of carbon dioxide you are releasing during the process of producing your metal. But I also realized that there was some form of methane being released in the process. So have you made any environmental consideration on that, which is going to, one way or the other, contribute to greenhouse effect? And also with your metal you are producing, at the end of the day, there's going to be a carbon content. How is that going to affect the quality of iron material we are going to produce? Thank you.
Yeah, thank you very much. So first to the diesel question about the process that is happening. Yeah, I hope you understand what is meant by pyrolysis. You heat your polymer in limited amount of oxygen or in the absence of oxygen. Now, in this process, we're talking about what is known as a catalytic depolymerization process. In fact, it is a form of pyrolysis, but it's not normal pyrolysis. If you watch the video critically, you can do a normal pyrolysis, but your normal pyrolysis may be said that you are producing only your gases. The gases that you produce should be able to be, you need to crack the gases. And by cracking, what I mean is that I am reducing a high molecular weight gas into lower molecular weight gases. That is what we call cracking. But this cracking is done very well in the presence of the catalyst. So it is a catalytic depolymerization. When you are forming the plastics from diesel, you do a polymerization process. That's why we call all these plastics polymers. But the reverse process, I am doing a deep polymerization process through a catalytic cracking. So question answered. Yeah, you were worried about the methane gas that is coming from the, is it the iron making facility? The iron making facility. The production of methane. I hope we are aware that methane, the effect of those gases on greenhouse gases is concerned, methane is more powerful than carbon dioxide. In fact, its footprint is higher than that of carbon dioxide. Now, the methane that we produce, you notice that we produce methane, we produce carbon monoxide, we produce carbon dioxide, and we produce some hydrogen. Now, this was done in the laboratory. Now, what is happening, or what is telling you is that I can rechannel those gases because they still contain hydrogen, which is still a reducing agent. They still contain carbon monoxide, which is still a reducing agent. And they contain some amount of methane. If you are if it is being your methane to change to carbon monoxide and hydrogen. Okay. So, and another the thing that the process is actually starting point material in the chemicals industry for the production of methanol and so on and so forth. I can redirect my methane, my hydrogen, my carbon monoxide back to the process, or I can send it to the national grid because I have syngas in them. In fact, gas analysis that we did after the reduction process showed that the gas content from the process is up to about 95% syngas. In other words, carbon monoxide and hydrogen alone. That there should be carbon dioxide. We do have some methane, but that is normally not too high. Okay, so it is manageable. And I can assure that the methane that is coming might not be lower than when you produce your iron from the normal processes like a blast furnace and then the like. Because in a blast furnace, when you have moisture, the carbon that is can combine with the hydrogen from the moisture to form methane as well. You mentioned that there is carbon in the iron. Yeah, the carbon in the iron is not higher than the carbon that is produced from the blast furnace. In the blast furnace iron making, you can produce carbon up to about 5% carbon. You can produce iron having about 5% carbon. And this process, the average carbon content is around 2.5, but you can move up to about 6%. Now the carbon in the iron is not entirely a disadvantage. In fact, if we get to the level in Ghana where we want to produce, for example, we want to avoid the steel making process, and we want to produce what is known as merchant iron, and then we can sell. Okay, then the carbon is an advantage. Carbon in iron is good for corrosion protection. I have produced iron as far back as 2010. Those iron metals are still there. They are intact. They haven't undergone corrosion because of the carbon that is there. When we get to a point where we are producing our iron and then the carbon is there and then we are shipping overseas, a ship may potentially take between 1 month to about 3 months along the oceans. If that carbon is not there, by the time you get to wherever you're going, your iron will. The iron that we have, the carbon that is in the iron, when you are moving from to the steel making stage, the carbon that is there is a reactive form of carbon. In steel making, you see those guys coming for the scraps and the scrap. For example, in electric arc furnace steel making, all they do is and then you oxygen through. The step where you oxygen through, any carbon that is there will undergo to form carbon monoxide. Come out. Because the oxygen is oxidation. So it is not an issue.
Thank you very much. I'm very inspired by your presentation and I'm in love with it. And the whole of Ghana thanks you very much. And yeah, to my questions. Now, we saw charts for iron. Okay, and I want to know that do you have any charts or presentations or researches done on these materials on other metals, such as aluminium and those other kinds? And then the energy. What kind of energy will you be using? Like, I know you'll be using heat. Will you be producing this from maybe the heat source? Will you be using electricity? And if you are using electricity, won't that be too much of an effect on the national production of electricity?
Please, I wanted to ask that sometimes you said we do education to tell people to separate the plastics and everything. But by all means, we'll have stubborn people who would not do it. Ghanaians especially. Yeah. And so please, when it happens that way, don't think we should encourage the use of biodegradable plastics too as well in the country too, so that the stubborn ones who would still be stubborn would not make it affect. Yeah.
Yeah. I'll take the first question. As to whether the process has been applied to other metals, the answer is yes. The answer is yes. You can read about some of the work I've done in those areas. When you just type my name, Dr. James Ransford Dankwah, you go to Google, you just type, some of them will come. Some of them are available free of charge. There are others that sometimes if you're not careful, they say come and pay before you get them. I have applied the same technology. In fact, I started with iron because when I was doing my PhD, it was on using waste plastics, iron making. I got there maybe because I was old and I knew what I wanted to get from there before coming back to Ghana. So during my lunchtime, when the others should go for lunch, I would sit there quietly and then try my technology on other metals. As part of the process was said that I asked some people to bring me some. I also got my own manganese oxide. I got manganese carbonate. I got all the oxides of manganese. I applied it to manganese, and I can assure you that globally, in terms of somebody using waste plastics to reduce iron, I would say I was the first person to produce manganese metal from manganese ores using waste plastics. The second paper that also came to reduce higher manganese ores to lower manganese ores. If I want to produce pigments like paints and then the like, sometimes manganese, the lower form of manganese, MNO, the color is green, and then it's used in paint making. I can go for any higher manganese oxide, like from GMC, and all I'll do is that I'll convert it to MNO, which is green, and then I can use it in paint making. I was able to produce the MNO using waste plastics as a reducing agent. I have applied the process to chromium because I know that chromium is also used in the iron making industry, in steel, the ferrochromium industry. If I want to produce stainless steels and then like I need chromium over there. So I've used waste plastics in chromium reduction. Currently, the guy who was bothering me over here was looking for me because of the ferrochromium work that he's doing. I have used waste plastics in upgrading of bauxite. If you hear that a technology has been developed in Ghana where value is being added to our bauxite, where currently we sell our bauxite at $30 per ton. So those big trucks that you see passing by, those yellow big trucks with bauxite, $30 per ton. 2012, 2013, I went to Egypt. I saw bauxite from Ghana in Egypt. It was being sold at $300 per ton. The grade was only 80% alumina. The bauxite that we have in Ghana here, the grade is from 45 to 60% alumina. So they buy it $30 per ton, and then by the time it gets to about 80%, the price increases tenfold to $300 per ton. That is still not alumina. By the time you get to metallurgical grade alumina, you would have moved from about $300 per ton, depending on the fluctuation, to an average of about $450 or $500 per ton. And that is why we are struggling in Ghana. Valco is importing alumina to produce its bauxite, to produce its aluminium, whilst we are selling bauxite for them to produce the alumina, so that we go to a world market price to produce, to buy the alumina and then sell. So Valco is operating only at 33%. The work we did in the lab was in 2015. All we did was that we wanted to see whether we can, if it is buying bauxite from China, and that bauxite is Ghana bauxite at $300 per ton at 80% alumina. We wanted to see whether we can do the same process over here. And I can assure you the work we did. We took bauxite from Awaso. Then we mixed it with waste plastics, heated it for just about 30 minutes. We were able to upgrade the bauxite from an average of 45% alumina to between 87 and 92% alumina. The technology is not rocket science. It's a very simple technology. Very simple. We did it in our labs over here. We don't have too much of any sophisticated equipment over here, but we're able to produce it. And we think that we can at least add value to our bauxite. Indonesia did the same thing to China about 4 years ago when they told them that we will continue to sell our bauxite to you, but help us with about 3 bauxite smelters so that we can also produce our alumina. Then even if we sell our bauxite to you, we don't go outside and then go and buy alumina. We can produce our own alumina. Then we need to produce aluminium. You stop buying bauxite from them for about 2 years, but later they came back. And as you speak, they have about 4 smelters built by China. We can do the same thing in Ghana over here. The good thing is that this technology can be applied to all the metals. So if you go to the periodic table, every metal that is there, if you want to produce it, you can use plastic as a reducing agent to produce the metal. You mentioned, that's question number 4, biodegradable plastics. Let me just summarize just in a sentence what was said about biodegradable plastics by the German resource persons who came to the workshop on 30th January 2018. It was simple. I will quote the statement from that white man. At this stage, we do not think that the use of biodegradable plastics is a solution to the plastic pandemic, unquote. I have always asked this question. How degradable are biodegradable plastics? We hear a lot of myths. I have a whole paper, a whole research that was done on biodegradable plastics. And I can assure you, the results are startling. How biodegradable are the so-called biodegradable plastics? I went to the minister's office in November, and he was saying, oh, we have some guys who are here to come with biodegradable. I said, I will not recommend. He was surprised, but I said it bluntly. If you venture into that, you throw money away. Our current throw away attitude, we take our sachet, we drink, and then we throw it away, thinking that it will disappear. For biodegradable plastics to biodegrade, you need to expose them to ultraviolet radiation. The way we mix our plastic waste and the way we throw them away. If those plastics are not exposed to the ultraviolet radiation, they will not biodegrade.